Hey everyone, welcome back. This will be part B of lecture 10. So we're in the middle of doing examples using the disk and washer method for calculating the volume of solids of revolution. And so here's another example. Okay, so I guess up until now, the examples that we did in part A were all examples where the axis of revolution was the horizontal axis, i.e. the x-axis. So in this example, we're going to rotate our planar shape about the y-axis instead. Okay, so find the volume of the solid formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. All right, so about the y-axis, this is going to be a horizontal axis of revolution. So let's plot this and get a look at the planar shape and see what kind of things we have to think about here. And so y equals x squared plus 1. So that's just a quadratic function with a vertical shift. So we'll say this is 1, maybe that's 2. Right, so this guy is just going to come up like this. Okay. All right, and so we're interested in y equals 0. So that's the x-axis. X equals 0, that's the y-axis, and x equals 1. And so we kind of know that this guy here is going to be equal to 2 at x equals 1. And so this is a reasonable picture of what this would look like. Right, and so the region of interest here is this. Okay, and we're going to be rotating about the y-axis. Right, and so you might imagine this is going to look a little bit like some kind of like a glass with a really thick base, perhaps. Okay, and so our representative rectangles will be oriented like this now. All right, and they're going to have width delta y. Okay, and the radius here is going to be this whole distance. Okay, so what is the radius then? The radius is 1, the outer radius. Right, this is going to be the whole distance, so our outer radius will equal 1. Okay. Now the inner radius, here's where it's a little bit tricky, right? So down here, the inner radius is 0, right? Because the representative rectangles down here are actually on the y-axis. Up here, however, the inner radius will be different. Right, so there's kind of like two spots here. There's above and below y equals 1 that have to be considered. Okay, so the outer radius, let's summarize here. The outer radius is simply 1. Okay, always. The inner radius has to be considered in 2 regions. Okay, so the inner radius has 2 different regions. Okay, so we could think of this as our region 1, and this we'll think of as our region 2. Right, and the reason there are 2 regions, just to reiterate, is because the representative rectangle in region 1 is always going to be, it butts up against the axis of rotation, right? So there r is equal to 1. Up here, however, the representative rectangle has an inner radius that is different, right? It's going to actually be based on this function. Okay, so in region 1, little r is equal to this function. But remember, this has got to be written as a function of x. So y is a function of x. So we'll say r is equal to the square root of y minus 1. Now, why do we say that? Well, we say that because y is equal to x squared plus 1, right? And so that's the function that's given, but that's y is a function of x. We need to do it the other way around, so we have to flip this around and do the algebra. So we subtract 1 and then take the square root, and we get x equals the square root of y minus 1. Okay, that's kind of a side calculation. So in region 1 up here, the little r, the inner radius, is square root of y minus 1. In region 2, that's this lower section, there r is equal to 0, right? Okay. All right, so the fact that there are two different regions and two different values of r depending on where we're at on across the partition here, that means that we have to have two separate integrals. Okay, so we need like a region 1 integral and a region 2 integral. Okay, so for region 1, that'll start, well, let's start with region 2. I kind of labeled these backwards. Maybe I should have called this 1 and this 2, but it doesn't matter. So we'll start with region 2, because that's the simpler of the two. So that'll be from 0 up to 1. Okay. Pi times the integral from 0 to 1. And then it's, remember, it's big R squared minus little r squared. Okay, so big R is 1 here, and little r is 0. Okay, so that's the first one, so this would be region 2. Again, I labeled them slightly backwards. That's okay, though. And then the second one will be another integral, and it'll go from 1 up to 2. Right? So that'll go from 1 up to 2. And there, the big R is again 1, so it's 1 squared minus, now the little r is different in region 2, or in region 1, right? So it's square root of y minus 1. Okay. There it is, right? So then this is the region 1 integral. Okay, so but once we have those, it's a simple matter of just calculating these. Okay, so let me get a new sheet of paper here. Start fresh. So the volume then is equal to, just rewriting this here, pi times integral from 0 to 1, and then it's 1 squared minus 0 squared dy plus pi times the integral from 1 up to 2, and it's 1 squared minus just like so, right? Okay, so big R squared minus little r squared. Big R squared minus little r squared. Okay, and we can calculate this really quickly. Right, so this guy here is 0 to 1, and it's just 1 here, right? So it's just dy. And now what happens here? Well, you've got 1 squared is 1, and then if you square the square root of y minus 1, you just get y minus 1. So it'll be 1 minus negative 1. So what you'd end up with for the second one here is 2 minus y. Okay, so then you just get y from 0 up to 1. And then for this one, you get 2y minus y squared over 2 from 1 up to 2. Okay. And so you can calculate each of these separately. So this will be 1 minus 0. And then what do we get here? We get 4 minus 2 minus 2 minus a half. Okay, so I have pi in the front, and then it's going to be plus pi, and then what do I have here? 4 minus 2 plus a half. So I get pi plus pi over 2, so 3 pi over 2 is the answer. Okay. right? So the volume of this figure then is 3 pi over 2, right? So just kind of keeping in mind what this figure would look like. It's going to kind of have a cylindrical shape on the outside, okay? But inside it's going to kind of do one of these, is it's going to have this kind of cutout. Actually, it would come down further. It would come down more like this. Okay. It's going to have this cutout inside. Okay, and the volume will be equal to 3 pi over 2. Okay, perfect. Perfect. Let's do one more example, I think. Maybe one more example. So for this example, we'll change the wording a little bit. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches. Okay, so that you get some metal sphere of radius 5 inches, and this manufacturer drills a hole through the center of the sphere. The hole has a radius of 3 inches. Okay, and then the question is, what's the volume of the resulting ring? Okay, so totally different kind of wording here. All right, so let's see if we can draw a reasonable picture of this. It's start with a sphere, okay? And so someone's going to come in here and going to drill a hole right through the middle of this thing. Okay, so it's just going to be a hole there, and it'll be on both sides. It's a terrible picture. It looks something like that, though, right? So, okay, so the idea here is that we can kind of represent this as a this can be represented as, even though we're not talking about explicitly revolving a particular function or a particular plane or shape or region around an axis of revolution, this implicitly meets the definition of a solid of revolution, right? And so in particular, if we rotate, if we have an axis of revolution right in the middle here, then this would be, we could kind of set this up using like a geometric shape here, right? So the way I want to think about this is that, so there's a circle, right? Basically, if we're going to create a ball in space, we're going to have to use a circle, right? Or a semicircle, right? So the circle has an equation of x squared plus y squared equals 25. Now, how do I know that? Well, this is just going to be a circle centered at the origin with a radius of 5, and so this equation kind of pops out of those parameters for the circle, right? So x squared plus y squared, that tells you it's centered at the circle, or centered at the origin, and then the 5 squared equals 25 tells you the radius. Okay, and so given this, we can back into a function, y as a function of x. We can say y is equal to 25 minus x squared, the square root of that. Okay, so this is going to be our outer radius. Okay, let's draw a picture here. Let's see if we can make this clear. Okay, so we've got, right, so this is our x-axis. This is our y-axis. Okay, so 1, 2, 3, 4, 5. So we're going to have a semicircle that's built around the origin and with a radius of 5. Okay. Now we know that the radius of the hole that is drilled into the circle, right? You're going to drill a hole right in the middle of the circle. It's going to have a radius of 3. Okay, so from here all the way up to here is 5. And the hole that we drill is going to have a radius of 3. It's going to have 6-inch diameter, but a radius of 3. So what that basically means is if we're going to rotate around here, right, then we're going to have 1, 2, 3. We're going to have this line y equals 3 come into the equation as well. So we've got y equals 25 minus x squared, and we've got y equals 3. Now this is the region, right? And we're going to rotate it around the x-axis. So you can imagine if we do that, we get something that kind of looks like this. This is a really bad picture, but it kind of looks like this. Right? It's going to have a hole right through the middle, and the diameter of the hole will be 6 with a radius of 3 therefore, right? And then this part here is going to be kind of the body of the ring that is generated here. Okay, so you can imagine what would happen if that sort of starts to flip around the x-axis. Okay, and so we've got our inner radius here. Okay, we've got our outer radius here. All right, makes sense, makes sense. Our representative rectangles are going to be, or set up like this, right? So you'll have your delta x here. All right, again, perpendicular to the x-axis, the axis of rotation. So what are the limits of the integral going to be? How do we figure that out? Well, we know that y equals, we're looking for where y equals 3 intersects x squared plus y squared equals 25, right? And so we could basically plug in a 3 for y, couldn't we? Right? We could plug in x, so we have x squared plus y squared equals 25, and so we can plug in a 3 here, x squared plus 3 squared equals 25, and so that's going to mean that x squared equals 16, right? So this would be 9. 25 minus 9 is 16. So x is plus or minus 4. Okay, so that means this here and this here, this is going to be negative 4. That's going to be positive 4. Okay, so our integral will go from negative 4 up to positive 4. Inner radius is found, outer radius is found. It's consistent throughout the entire the entire shape. We don't have to have multiple regions, so we can set this integral up now. So the volume will just be equal to pi. Again, writing the formula a to b, it's r of x squared minus little r of x squared dx. Okay, so plugging in our actual values, negative 4 to positive 4. Okay, and then our outer radius is 25 minus x squared, so it's the square root of that, and we want to square it, minus our inner radius, which is 3. Okay, and then it's all integrated with respect to x. All right, so that's the setup here. Let's go through quickly and calculate the integral. Okay, so the volume here is equal to pi times the integral negative 4 to 4. And I'm just going to rewrite it really quickly. Okay, just so we have it all on one page here. And so obviously the square root and the square go away, so it's pi times the integral negative 4 to 4, and then it's 25 minus x squared minus 9, like that. 25 minus 9, right? We do that, and we get negative x squared. And what is 25 minus 9? Well, we just did it, 16. Okay, then we can integrate this, and we get negative x cubed over 3 plus 16x. Okay, and that goes from negative 4 up to positive 4. All right, and so then we can plug all of this in, and And so it's pi, and then it's going to be kind of some biggish numbers, but so it'll be negative, and then it's 4 cubed over 3 plus 16 times 4. So that's the first one, and then we subtract off of that the whole thing evaluated with the negative 4. And so it'll be the same thing, similar anyways. Don't forget the negative signs everywhere to make a pretty big difference if you do. Okay, and then we get, what do we get here? So this would be negative 64 over 3. And this would be 64. And then it's going to be, again, a negative 64 over 3 here. And this will be, this will be minus 64. And so, it's taking a, so altogether we will, we'll kind of want to get common denominator of 3 here, so you get 192 minus 64. I'm kind of rearranging these a little bit. All over 3 minus, and then here you'll get negative 192 plus 64 over 3. And you get pi times, this would be 128, yep, over 3, plus 128 over 3. And so you get 256 pi over 3. Nice. Okay. All right, so there's that last example. So we found this volume of this ring that's formed by this section of a semicircle rotated about the x-axis. Okay, and what we found was that that volume is 256 pi over 3. Okay. All right, so that's where we'll end this section. And then the next video we're going to talk about, or the next lecture we'll get into an alternative method for finding volume of solids of revolution. It's called the shell method. Similar in style, but just a different construction. Right, so the shell method will be next, and all right, that's where we'll leave it.